You're listening to Episode 3 of The Star Spot for Friday, April 20th, 2012.
I'm Justin Trottier, and I'll be your host at The Star Spot. The Star Spot is a space-themed podcast that focuses on all aspects of astronomy and space exploration. Episodes feature interviews with guests of wide-ranging backgrounds: scientists, engineers, educators, artists, politicians, and business people. Topics are similarly broad, from the latest space mission to how the universe began, from why humans explore to how we can make exploration economical. We'll also include a segment called Current in Space, bringing you reports on news and developments that may interest the space enthusiast. Our feature interview today is with Dr. Carolyn Porco, planetary scientist and head of the imaging team for the Cassini mission to Saturn. But first, Amanda Gadke brings you what's current in space.
One last hurrah. On the morning of Tuesday, April 17th, starting just after dawn, Space Shuttle Discovery had one final adventure, flying on the back of a Boeing 747 from NASA's Kennedy Space Center in Florida to Washington Dulles International Airport. On its way, it spent 45 minutes flying over Capitol landmarks, including the White House Rose Garden, the tip of the Washington Monument, the dome of the Capitol, and the National Mall, as well as tens of thousands of onlookers, some of them in costumes. It also flew over the Arlington National Cemetery and the graves of astronauts killed in the 1986 Challenger and the 2003 Columbia Space Shuttle tragedies. Discovery's own final resting place will be the Smithsonian's National Air and Space Museum's Stephen F. Udvar-Hazy Center in Virginia. Starting with its maiden flight, STS-41D, on August 30th, 1984, the flagship space shuttle flew in space a total of 39 times, more than any other NASA craft, with accomplishments under its belt like International Space Station assembly missions, the delivery of the Hubble Space Telescope into orbit, and hosting the first Russian cosmonaut on a U.S. spaceship, all culminating in over 148 million miles of travel, or the equivalent of a year's worth of days in space. With the Space Shuttle program retired, the U.S. can no longer launch astronauts into space for the first time since 1981, and will have to pay large sums to get access to the ISS via Russian Soyuz capsules. Meanwhile, NASA turns to financing the private sector to fill the gap, starting with space station cargo and later, if all goes according to plan, astronauts. SpaceX, a company out of California, is aiming to make history by being the first private company to launch a craft called the Dragon to dock with the International Space Station at the end of this month.
My guest today is Dr. Carolyn Porco. Dr. Porco is a planetary scientist who led the imaging team in studying and interpreting images from the Cassini-Huygens mission to Saturn and its moon Titan. Dr. Porco is a senior research scientist at the Space Science Institute in Boulder, Colorado, and she's adjunct professor at the University of Colorado and the University of Arizona. Her scholarly work, as well as her efforts to convey science education and literacy to the public, has won her many awards and recognitions. These include the Carl Sagan Medal from the American Astronomical Society for excellence in the communication of science to the public, and in 2008, Wired magazine named her one of 15 people the next president should listen to. Dr. Carolyn Porco, thank you so much for joining us at the Star Spot.
Thank you for having me.
So I guess I just want to ask you right off the top, do presidents often listen to planetary scientists? And if not, should they be doing that?
I've never heard of a president listening to a planetary scientist, although actually I take that back. I think that Jimmy Carter, in fact, had a conversation with Carl Sagan when he asked Sagan to, he thought it would be a good idea if Sagan wrote a book, I think it had to do about a nuclear proliferation. And Sagan, of course, said back to him, but all you have to do is sign your name. So there has been a recorded conversation between a president and a planetary scientist, but I don't think it happens often.
So the precedent has been set. Dr. Porco, let's start sort of with your early life. When did you first realize that you wanted to be an astronomer or a planetary scientist?
Oh, when I was a young teenager. So I was in high school. There was a confluence of things that happened. I was brought up in the 1960s. So remember, the 1960s were a very spacey time. You know, we were making plans to go to the moon, and there were lots of shows on television, Star Trek and Lost in Space and so on. So the whole culture was absorbing the idea that we were going to be a spacefaring culture. But I also was going through something of my own. I was a very introspective young teenager and thinking about big questions like the meaning of life and what was I doing here and what was the meaning of my own life. And that got me thinking about, well, what am I doing here? Well, what's here? Where are we? And that got me looking outwards and trying to understand what our cosmic context was, if you will. And so I began reading about astronomy and cosmology and so on, and that got me into astronomy. I'd always been interested in science from a rather young age. I was always curious about the natural world, but that got me turned into the direction of things astronomical.
You're most well known for being connected to the Cassini mission to Saturn, so I wanted to ask you, for something so large and complicated like that mission, how much thought and planning and, well, I suppose bureaucracy goes into something of that magnitude?
A huge amount. Just a colossal amount. First of all, we have to plan everything many years in advance. And for outer solar system missions, you have to plan it many years before you arrive. So, you know, the mission got its first start in late 1990. That's when all the scientists were called together, were chosen. I was chosen to be the imaging team leader on November 13th. I got the phone call November 13th, 1990. And then, you know, we basically started in earnest to plan the Cassini mission then. But actually the idea, the conception of having a mission that would return to Saturn after the Voyager flybys in the early 1980s, that goes all the way back to the 1980s. So the idea of returning to Saturn with an orbiter mission began in the 1980s. The mission got its first start in 1990, and we didn't launch until 1997. We didn't get into orbit around Saturn until 2004. And this is not unusual for outer solar system missions. A colleague of mine once said, you have to enjoy the process because it takes so long before you enjoy the fruits of your labor.
So the idea to return to Saturn, that concept, that began almost as soon as Voyager started reporting back its data and images?
Yes, remember Voyager completed its tour of Saturn, of Jupiter, Saturn, Uranus, and Neptune, the major planets in the outer solar system, in 1989. But even before that, we were all talking about what we would want to do with a mission that returned to Saturn and went into orbit.
Were there mysteries that Voyager produced through what was coming back from that particular mission, that the feeling was these mysteries need to be explored and solved in subsequent missions?
Oh, of course. That's always the way it goes, is it not? I mean, Voyager was our first cursory look at the Saturn system. Yes, the Pioneer spacecraft had been there before Voyager, but they were really spacecraft that were designed to tell us whether or not a spacecraft could actually make it through the asteroid belt and live in proximity to the giant planets, which had we knew Jupiter, for example, had a very healthy magnetic field. And so Pioneer was just that. It was to see, could a spacecraft survive there? And it had a rudimentary camera. So we didn't really get a very good visual look at what was in the outer solar system until the Voyagers. So the Voyagers opened up the solar system to us, really. I mean, it's not hyperbole to say that they showed us what the majority of the solar system looked like by opening up the outer planetary systems to our view. But they presented as many questions to us as they answered questions. You know, it just told us basically what the major components of the system were. We only spent a week or two within the Saturn system or with any of the planetary systems that it visited. And so we had lots of questions that remained. We never even got, for example, just one example, we never even got a good look at the Titan surface with Voyager. Titan was as much anticipated with Voyager as we anticipated it with Cassini. But it turned out the spectral properties of the Voyager cameras were exactly mismatched to the scattering and absorbing properties of the Titan atmosphere, so we never got to image the surface. So there were a lot of questions about what the surface of Titan, one of the most fascinating bodies in the Saturn system at the time, what it looked like. And so we wanted to investigate that, and we wanted to know more about the rings. We got close-ups of the rings, but not enough to really understand what the details of the physical processes ongoing there were. So we wanted to study the rings in greater detail, and then, there were lots of other things about the atmosphere and the other moons that we wanted to find out about. The goal was basically to understand the breadth of planetary processes that were at work in this very, very complex planetary system, because we always stand to learn a great deal about our own planet and the planetary processes at work here by having other examples to study. So Saturn and everything around it presented great opportunities to test and refine our notions about all those kinds of planetary processes. So we were very eager to go back with an orbiter mission.
And you mentioned Titan as being one of the objects you were especially interested in returning to. So was the inclusion of the Huygens probe, which of course landed, albeit briefly, on the surface of Titan, was that probe seen from the get-go as a vital component of the Cassini project, or was it introduced somewhat later in the planning?
Oh, no, I think it always had been there as a vital component, yeah, because Titan, as I said, it was just a fascinating body. We'd known for years it had an atmosphere. There was all sorts of speculation about what might be going on its surface, and we were very eager to find out. And we knew from the Voyager data collected by other instruments besides the cameras that the conditions were such that methane could be liquid on the surface. Maybe even nitrogen could be liquid on the surface, although later on we realized it was probably not the case. And if anything was liquid on the surface, it was most likely going to be methane. And so it just, it just was really fascinating to think about what we might find there. And bear this in mind. This is one of those historical footnotes that's just very, I don't know, it gets me when I think about this, that before Cassini arrived at Saturn, Titan presented to us the largest single expanse of unexplored terrain that we had remaining in our solar system, right? We hadn't seen its surface, and it was all there waiting for us to explore. And now that we've seen most of its surface at even if it's limited resolution in some places, we still have seen, I think, the whole entire surface of Titan. And there's no other body in the solar system now that presents to us that much unexplored terrain.
So the Cassini team itself was selected as early as 1990, and as you've said, this was a long-duration project, I suppose over 20 years in duration, including 7 years of travel time waiting for the spacecraft to arrive at its object. How do you stay focused and disciplined on a project of that length?
Well, there's a lot to do. I mean, there's an enormous amount to do preparing the spacecraft, designing the spacecraft, and designing the instruments. Okay, that's a major enterprise because you have to first understand exactly what it is, what questions are we going to ask, what questions do we want answered when the spacecraft arrives there. Right. So that plays into what kind of capabilities we need all the instruments to have and what kind of capabilities we need the spacecraft to have. And then there are also engineering criteria that have to be applied to all these instruments. So, just melding that all together to come up with a design that meets everybody's expectations and does what we want it to do and will live for the required amount of time is a huge effort. So we spent 7 years doing that before we launched. And then once we launch, we have to figure out, okay, so now we're on our way. Now we have to figure out when we get there, what kind of tour do we want? What does the trajectory of Cassini over 4 years, and then after the nominal mission is over, any years beyond that, what will that tour, the trajectory, look like after we get there? And that's a major, major effort as well, because now we're getting down to brass tacks. Now we're saying, okay, the ring people, the people who are interested in planetary rings, they want the spacecraft to be up out of the equatorial plane, looking down on the rings. And they need that to happen at certain periods of time because certain periods of time present unique opportunities for looking at the rings. But those people interested in observing the moons, for example, they want the spacecraft to be in the equatorial plane because that's where the moons are. They're in the equatorial plane. So if we want to have very close flybys of the Saturnian moons, then for the most part, those flybys have to occur when the spacecraft is in the equatorial plane. It turns out not always. We can dive down from the polar regions, from up above and below to get close to a moon and thereby see the moon's polar regions. But for the most part, we're in the equatorial plane to visit the moons. And on it goes. The people who want to study the atmosphere, they put requirements on the tour, and people who want to study the magnetosphere, they have their own requirements, and this is like a big optimization problem with hundreds of people involved, hundreds of discussions and telecons, and then finally we arrive at a tour, which of course is designed by the mission designers at JPL, who are excellent, by the way. And finally we arrive at a tour and we know, okay, at this point in time, at this month, or this year, month, day, hour, and even minute and second, we know exactly where Cassini is supposed to be and what object it has in its view, and then all the instruments start arguing now about what they want to view at any one point in the tour. And that's a big, long process. And by the time that's over, we have sequenced, that's what this is called, sequencing. We have sequenced the whole nominal 4-year mission, let's say, down to the nearest minute. Now you can imagine how much time that takes. So and then of course, for someone like me, and I was responsible for the imaging experiment, I had to make sure that we had all the software we needed to command the cameras. We had to have the software ready to do calibration of the cameras, and we had to build our own databases, and then I had to build software that would allow us to process the images and release them to the public. So this is a gargantuan effort, and we were busy every step of the way until we got into orbit and many years later, and we're still busy now. So, when you say how do you stay focused, it's the problem is not staying focused. The problem is finding some time to relax.
I think I can appreciate that. When you were talking about how complicated the system is, I really wanted to ask you about how you build in that versatility from the preparatory stages, because while you're exploring, you're also making discoveries, you're finding new moons, you're finding all sorts of interesting things in the rings. How exactly was the mission planned from the beginning so that it would be able to respond as these discoveries were being made?
Okay, well, first let me say that is the advantage, the primary advantage of being in orbit and having the leisure to know that if you discover something, you could, in principle, at a later time, go back and investigate it. You can't do that with a flyby mission, right? So that's one of the reasons why we want to stay in orbit. You can do a far more comprehensive and in-depth, thorough survey of something by being in orbit, right? We've just taken up residence at Saturn, and we can look, whenever we want to at something. But you're right, we have to build in adaptability. And at first we do this by just knowing that, when I said we sequence the mission down to the nearest minute, well, we left some gaps because we knew, well, at this point in time, if we had discovered a new moon, or if we had discovered some new feature in the atmosphere of Saturn, or if there were clouds in the atmosphere of Titan that we wanted to see, this would be a good time to see them. And so we leave gaps in the timeline, and we know that, okay, those gaps, we'll have to figure out what to put in those gaps no later than 6 weeks before, something like that. And so that's far better than having to know 6 years before we get into orbit what we're going to be looking at. So we did build in adaptability in what we came to call retargetable observations. We could change the target of these gaps, or put in the target in these gaps far later in the mission than we could the majority of the observations. And this worked like a gut. You know, we could take observations. We could take our observations of new moons, our discoveries of new moons, for example, and when you first discover a moon, you have some very rudimentary knowledge of its orbit. And with that rudimentary knowledge, we can plan to go back and look at the moon again. And if our rudimentary knowledge wasn't too far off, we would have captured it, let's say, in a mosaic of images that covers a certain region of space where we expect the moon to be. If we see the moon, we put that into the pot, we fit another orbit to that new collection of data, we get a more refined orbit out of it. We can use that refined orbit to predict later on where it's going to be, and we take one of our retargetable observations and use it to look at this moon, and thereby we observe the moon, we refine the orbit yet again, and then the next time we're in a better position to know where it is. And we've done this now so much that we have exquisite knowledge of where all our discovered moons are, and even better knowledge of where all the moons that we've known to be there for years, where those moons are. So we have exquisite knowledge about where everything that moves that we've observed in the Saturn system is. And I could literally go on my computer where I have a program that tells me at any one moment what Cassini can see, and I can tell you where all these objects would be. So that's what we've done with moons and with cloud systems and so on.
Gotcha. So the Cassini mission, I mean, from what you're saying, I mean, obviously it really revolutionized our understanding of the Saturnian system. On the topic of moons, how many total moons have we discovered so far at that system?
Well, I can't even answer that because I've lost count. I know there are over 60 moons now in the Saturnian system, maybe it's 61, but Cassini's not the only one discovering moons. Remember, Cassini is orbiting in the inner Saturnian system. There is also a collection of moons about 10 to 20 million kilometers out from the center of Saturn. Cassini orbits within a 1, 2, or 3 million kilometers of Saturn, but at 10 or 20 million kilometers, there's the irregular satellites, and ground-based astronomers are actually discovering moons in that system. So Cassini, I think, has discovered 7 or 8. I don't even remember. I mean, my team has done the discovering here, and I can't even keep count.
And is it fair to say that more moons could still be discovered as we go forward?
Could be, but they would be very tiny probably by this point, and we're not exactly planning images to search for more moons. Well, I guess some searches are being done, but we're not scouring the whole entire system anymore because we think we found the ones that were easily seen, and now we're concentrating on more pressing scientific issues like, how do the seasons changing in the Saturn system affect the distribution of liquid hydrocarbons on the surface of Titan. So there are other things we are concentrating on now in the extended mission, much more so than we're looking for new moons.
Gotcha. And I think one of the mysteries or one of the questions that you were hoping to solve was why it was that some of the moons were rich in things like silicates and organics, but the rings tended to be more pure water ice, and why that difference, how that originated, why that exists. Is that one thing that you were able to resolve or shed some light on in this project?
Well, first, let me be clear. The moons do have silicates and organics within them, but I wouldn't say they're rich in them. They're still largely water ice. Mm-hmm. Enceladus and Titan probably have the most, relative to their own masses, probably have the most rock in them, but they're only about 60%, 50% rock,
right,
around that. But it's true, the rings don't have any. And so that has been an issue that is a puzzle, a big puzzle. And, the age-old idea for how the rings formed was, the one most commonly accepted was that it was a pre-existing moon, or maybe a captured object from the outer solar system, like the Kuiper Belt, that got caught up in the orbit around Saturn and got smashed up eventually, or got tidally sheared in the case of a captured object. But if that was the case, and if the body had been, let's say, a moon around Saturn, you might have expected it to be differentiated or have some silicates in it, and we don't find those in the rings now. So a recent idea has been proposed by Robin Canup and Bill Ward that it could have been a body of satellite in orbit around Saturn, something probably Titan-sized, and we know there's one Titan object in the Saturn system, so maybe very much earlier in the history of Saturn there were other Titan-sized bodies that formed, and they got dragged in by tidal forces in a disk, within a disk of material around Saturn. So that would have been tidal drag and gas drag and so on that would have dragged a moon into Saturn, but on the way in, the outer shell of it, with the icy shell, would have been ripped apart, and that would have gone into orbit around Saturn, while the rest of the moon could still have been dragged in. So
I see.
that has been a new idea for how you could explain why the rings don't have silicates, but we suspect the moons do.
You also made some remarkable discoveries, maybe some of the most exciting discoveries about the moon Enceladus. I'm curious how much we knew about this moon before the mission, and just how drastically our impressions of this moon changed with respect to what we were discovering.
Well, Enceladus has just been a mind blower for me. I mean, it is to me become the biggest thing we have found, not only at Saturn, but I think in the solar system, because it presents to us, we strongly suspect, the most accessible habitable zone that we have in our solar system. We knew from Voyager days and earlier that Enceladus was special. We knew that it had a surface that told us it had been geologically active in the past, because it wasn't completely cratered over like many of the other moons in the Saturn system. And if it's completely cratered over, then you suspect it hasn't had much of its own internal activity, because internal activity affects the surface in a way to normally to erase the cratering record, at least in some regions. And in Enceladus, in Voyager images, it looked like some regions had been completely erased. Many regions, a large fraction of the moon's surface had been completely erased of craters. So that told us, despite the fact that it was very small, only 500 kilometers across, so about the size of Great Britain, that it had been internally active, which we didn't at first suspect for such a small body, but there it was, staring us in the face. So something had happened to Enceladus internally to erase its cratering record. That made it very intriguing. And then it also had an association with the E-ring, which is this very diffuse donut-shaped, squashed donut-shaped ring that is coincident. The center of it, the place where it's densest, and it's very diffuse to begin with, but the place where the most tiny icy particles exist is at Enceladus. And then it kind of spreads out to the other moons as well. But Enceladus seemed to be the controlling factor, because the ring is coincident with the orbit of Enceladus. So there were obviously ideas put forth as to how the E-ring was formed. Some ideas said that it was charged particle bombardment into Enceladus that released its tiny particles, tiny ice particles from its surface and set them into orbit around Saturn. But there was another idea, truth be told, that was presented, that perhaps there were geysers or jets of some sort. Geysers, I guess, was the word used, I think, that came maybe from liquid water under the surface of Enceladus, and they were spewing icy particles into orbit around Saturn in that way. So it's not like the discovery of the jetting phenomenon at the south pole of Enceladus was completely a total surprise. That's untrue. That seems to have worked its way into the culture, but that's not really true. In fact, our first observations up close of Enceladus, when we knew we were in a proper geometry to look for such things, we even called them plume. You know, we name our observations, and they were even called plumes, because it was a search to see if any plumes of material were coming from the surface of Enceladus. And in fact, those were among the first images we had in which we did see something coming from the surface. It was a little bit ambiguous at first, but, you know, history will record those were the first images where we saw for sure something coming off the surface of Enceladus. what was so surprising was the magnitude of the phenomenon, how extensive in number and in surface area coverage and in sheer just phenomenological, impression that it makes on you when you look at it. That's what was just a mind blower to us. So we suspected something like that might be going on, but what we found actually still was far greater than we expected. And now, after being in orbit for 8 years and having looked at Enceladus for 7 of those years, and having data from other instruments to throw into the pot, and then having theoretical examinations of what might possibly be going on, we're fairly confident that these jets, first of all, that Enceladus has at least a subsurface liquid sea underneath its south pole, maybe an ocean, a hemispherical ocean underneath the south pole, and cracks in the surface through which the liquid water from this surface can erupt and make its way to the surface and turn into the phenomenon that we see. So, and of course now we know that what's coming out of the surface is also laced with organics. The icy particles that we see in our images, in fact, are salty. They apparently have the same salinity as the Earth's oceans, and that tells us the water that they come from is in contact with hot rock. So it's fascinating. It's everything we'd hoped we could find. As a planetary explorer, you just wait for the day when you can find something like this, because it is probably the most exciting, maybe even the oldest question that humanity has asked. Is there life elsewhere? And we think that Enceladus presents to us a place where we might actually find that life has taken hold. And even though there are other places in the solar system where we think life might possibly have taken hold, like the subsurface of Europa, Enceladus's habitable zone is far, far more accessible. All we have to do is fly through it with the proper instrumentation, and we can ask a whole host of questions that would address the question as to whether or not there are pre-biological processes going on, and maybe even if life has started there. So I've become a gigantic fan of Enceladus, and really impressing for people to be thinking about going back there with another mission, a flagship scale mission that can ask the questions whether or not there are biological processes going on there.
It's extremely exciting. I guess the moon Titan probably not quite so hospitable for life, but still the Huygens probe descent event was probably one of the most anticipated events in the history of the mission. Why was the touchdown on that particular moon seen as such an important event?
It was a time when humans, we could say we landed on the surface of a moon in the outer solar system. I mean, that's pretty heady stuff, something that we had actually made contact with the moon in the outer solar system. And of course, we had sent the Galileo spacecraft into Jupiter, but it just didn't have quite the same feel.
Right.
We landed something and it took pictures for us, it obeyed our commands. It was really like we had touched it and we had been there. And you could imagine you had been there because of the pictures that it returned. And what it told us scientifically was mesmerizing. We had been watching Titan for months up until that point. We're talking now about mid-January 2005. Well, the orbiter had been taking pictures. My team and I had been taking pictures of the surface of Titan for months by that point, and hadn't really been able to make out anything on the surface. We'd seen very hazy features, shades of white and black and gray, and it was, in places it looked like we did see meandering channels or something, but we couldn't be sure. We couldn't see any craters, so that told us the surface had been reworked in some way. But it was really the images from the Huygens probe that gave us unambiguous evidence that liquid had flowed on the surface of Titan and had created these dendritic drainage patterns. And I mean, how exciting was that? We had suspected there was liquid on the surface of Titan, which told us we might see geological landforms that were similar to what we see on the Earth made by liquid water. We knew that there could possibly be rainfall, and we might find ponded liquid hydrocarbons. So it was tremendously exciting to see those images from the Huygens probe, because we did see evidence of all of that. I mean, not standing bodies of water, but evidence that liquid had flowed there. And that actually helped us a great deal in interpreting the images that we were seeing from orbit. So for historical reasons and also for scientific reasons, it was just a very important moment in the history of the mission.
You tell these stories of science so eloquently, and in our last few minutes, I wanted to talk to you a bit about science, sort of as storytelling, because you do a lot of public education talks, trying to increase the public awareness and understanding and appreciation for these amazing projects that you're involved with. And I had seen one of your talks where you made the claim that Hollywood does a great disservice in its treatment of science and scientists when it tells the stories of science. Can you explain how you mean that?
Well, I've been since corrected. People tell me Hollywood actually these days isn't doing so bad a job. I don't watch many movies and television, but there was a long, long time in the history of Hollywood when, they used the scientist as the evil guy, or the scientist as the nerd, the inept social nerd, as if they ever put a scientist in their pictures, in their movies, that's the role the scientist filled. Think of the scientist in Back to the Future, who was a great character, by the way, but just the crazed, obsessed, socially inept person, and forever, or the evil German, scientist, almost always had a German accent, right? I think maybe now things are changing, but I still think that Hollywood doesn't do enough with science, and with scientists. There's a whole universe of storylines they could be using to, in using scientists and the quest for the truth, which is, after all, at the heart of scientific inquiry. A talented storyteller could do a great deal with that. Instead of just using the standard boy meets girl romance, or, the murder mystery, or the political intrigue, or what have you, they could use the quest for the truth as their basic theme and build on that. And I think that it would vastly improve the public's impression of what science is and who scientists are, if storytellers would take that as the grist for their stories.
They often say that a picture speaks 1,000 words, and a lot of what you do is interpreting images. In our last interview on the Star Spot, we spoke to somebody who images exoplanets. Again, getting back to the idea of storytelling and perhaps with imagery, why, Dr. Porco, do you think there's something so appealing to us about images of other worlds, other moons in our own solar system, images, obviously they're just dots right now, of exoplanets in far-off solar systems? What is it about the images that's compelling for us humans?
Oh, because it just directly gives us a feeling of being there. Right? I mean, we hearing something from there doesn't do it, and we can't smell it, but we can see it. And for me, I think for everybody, it's just you feel like you're there, and that's what it does. It just immediately connects. It gives us a sense of immersion and engagement that we wouldn't otherwise have. And so I do very much feel that I've been, kind of living in the Saturn system for the past decade or more, because of having to be thinking about what we're going to do when we arrive there, and finally arriving there and seeing what we've seen. And it's, from the very beginning, really from the very beginning, from November 13th, 1990, when I was first selected to be the team leader, I had as a cardinal goal of mine to give the public, through the presentation of our images and the special treatment of them that we give them here, I wanted to give everyone who cared to even look at what we found in our images, I wanted to give them a sense of being along for the ride, a sense of the adventure, because it'll be a very, very long time before humans ever really physically get to Saturn. But, by proxy, we are there, And that has been, I think, the glory of all the hundreds of thousands of images we have taken. And it's pleased me that a lot of people feel that too when they look at our images. I'm very proud.
Absolutely.
It's been a privilege to be in this position, and I will die a happy woman knowing that I've left behind this treasure trove and legacy of exploration through our images.
Of those hundreds of thousands of images that these missions have produced, I know one that's special to you, and I think it's absolutely breathtaking, is Saturn eclipsing the sun, and you can see a little blue dot, which is us, which is Earth. I want to be a little provocative in one of my final questions for you, because I've watched some of your talks, and you describe so powerfully that sense of awe and wonder that you get from this kind of work. Would you almost describe your scientific quest and these discoveries as something akin to a spiritual experience?
Oh, absolutely. And by spiritual, I don't mean something religious. I mean that deep yearning that all of us have for a connection to something greater than ourselves, which, as far as I'm concerned, drives religious people to be religious. But for people who are inclined scientifically, it drives us to understand what connects everything around us. What are the physical underpinnings, the workings of the natural world? And I think that, when we see Saturn, especially when we see Saturn in that incredibly unusual picture, seeing it in a way we'd never seen it before, and then in the background to see the Earth, it gave us an immediate sense of cosmic place, and how we are connected to the solar system, to other planets, and yes, I think it gives us a tremendous spiritual connection in that sense. I mean, I can look at that and I see a lot of things. I've said this before. First of all, I see us as a species that is positively unyielding in its pursuit of knowledge, and very brave and yearning in its desire to understand the meaning of its own existence, because that is part of why we want to even explore a system like Saturn, to understand where we came from. And also I see the very best that we have to offer, because to be so small and reach so far, all the way out to Saturn, I think is what makes us special. And so there is that feeling of, unity with everyone else on Earth. So it's a feeling of connection with all other human beings, both present and past, and a feeling of knowing our cosmic place, where we fit in, that we get from looking at that one picture. So that by the way, is, I think, Cassini's most beloved picture by everybody.
Oh, certainly agreed. I guess for my last question, can you just give us a hint of what's to come for your work and the mission to Pluto that you're now involved with, New Horizons?
I'm not the lead scientist any longer on the New Horizons mission, because I've had to step down from that to concentrate on Cassini. And I've only been really my involvement in that so far has been very limited. I'm very much, however, looking forward to seeing what the surface of Pluto looks like, and its moon Charon and its other moons. Insofar as Pluto is really a prototype, if you will, for what's in the Kuiper Belt, it's going to be a historic mission. Even if it is no longer considered a planet, which it really should not be, it's still a very important piece of the solar system, and it'll be great to see it. And there'll be, I think, some sense of completion when we go by Pluto. But for me, I'm going to continue working with our images here. I'm very interested in Enceladus. I'm leading up an investigation of the jetting phenomenon, determining where they are, doing a survey of their positions, understanding what gives rise to them. And then I'm also going to be doing more lecturing, writing, perhaps doing documentaries. I want to spread the word about what we have accomplished, what humans have accomplished over the last 50-plus years of exploring the solar system and what it has told us and where we go from here. So that's in a nutshell what I plan to be doing.
Dr. Carolyn Porco, I want to thank you again so much for joining us here at the Star Spot.
Okay, thank you for having me and giving me the opportunity to wax on.
Thank you for joining us at the Star Spot, Mind and Universe Continually Expanding.
The Star Spot with Justin Trottier is an astronomy and space-themed podcast based out of Toronto, Canada. Please send comments or questions to starspotpodcast@gmail.com. The Star Spot is produced by Yingzhang Li, marketing and promotions by Natalie Morkos, guest news and voiceover by Amanda Gadke, research by Alexander Gurovich, web design by Blair Renault, graphics by Carmina Svillins. And I'm your host, Justin Trottier. Thank you for listening.